right, I'm going to go ahead and close the poll. And John, it looks like about 7% are not at all familiar with SSAS, 29% slightly, 42% somewhat, and 22% are very familiar with SSAS. So it looks like you have a very diverse group today. I'm going to share that with everyone. And we'll go ahead and hide that. And John, if you're ready, I'll go ahead and make you presenter, and I hope everyone has a great session today.
Okay, thanks. Okay, everybody should see my screen come up in just a minute.
Yep, there we go.
Okay, thank you.
Sorry to interrupt. If there's any questions that pop up, do you want me to go through those with you during, or do you want to do all the questions at the end?
Let's hold the questions till the end, I think. I should have enough time at the end to address anything that comes up.
Okay, sounds great. Thanks.
Okay, so today we're going to be talking about some advanced topics in analysis services, specifically about how to make sure that your processing performance is good, particularly as you start getting into larger and larger sizes of cubes. The processing windows become more and more important. The more data that you have, the longer it takes to process. Most companies these days are seeing vastly expanding amounts of data that they're collecting. Particularly with the new move toward big data in a lot of companies, the size and the volume of the data continues to grow, and thus your processing window for analysis services continues to grow. At the same time, that data also has to be moved around through ETL processes. So often I'm seeing companies find themselves with a little bit of a conflict of the ETL time is taking longer because so much data is being moved. The analysis services processing time is taking longer because of how much data is being processed. And those two things start to crowd each other. So today we're going to focus on how you can make sure you get the best performance out of your analysis services processing. Keep those processing windows small so that as ETL times take longer, you still have room to get things done within the established windows that you have for processing your cubes. So we'll be talking a little bit about the internals of processing, an overview of what's actually happening when you process an analysis services cube. We'll talk about tuning the process a little bit. So what are the steps that you want to follow as you go through this? And then we'll look at some specific bottlenecks that a lot of companies encounter, and we'll look at two aspects of this. What are some bandages that you can use? These are things that are more in the category of a quick fix. You might be able to apply these without having to make any major changes. And then we'll look at a second category of things that are more like doing surgery. So this really goes in to fix the root of the problem, but it requires much more in-depth changes to the way the cube is structured, and thus is probably not something that you're going to go in and apply over a weekend. It requires a little bit more work. The interesting thing about this is if you're listening to this, you may be thinking, well, great, that applies if I already have a cube, but I want to know what to do as I design my cube. A lot of the things that we talk about in the surgery aspects also apply very well if you're designing a cube. In fact, these are things that are much easier to do during the design process itself versus trying to implement after the fact. So if you're building new cubes, pay particular attention to those items and consider whether they might fit your needs either now or in the future. So just a little bit about me. I'm a SQL Server MVP and an analysis services maestro. I've worked on a few books around these topics, and I've been working with SQL Server pretty much ever since analysis services became part of the product. My contact information is there. If you need to get in touch with me, please feel free to reach out to me on Twitter or via my email, particularly if you have questions that come up post this presentation. So dimension processing. To go into kind of an overview of this, the four steps that make up dimension processing are building attribute stores. So the attribute stores are what contain the actual member values in the attributes of a dimension. Then we have hierarchy stores. We have decoding stores. Hierarchy stores store the hierarchy of membership, so user hierarchies and things like that. That's where this information is captured. Decoding stores are what allow analysis services to quickly traverse the hierarchies. So it allows you to look up higher level members of a hierarchy based on the identifiers for lower level members of a hierarchy. And then finally you have the bitmap indexes that again are there to accelerate the lookup of information within the dimension. So let's take a closer look at building the attribute stores. So if you have a typical customer dimension, perhaps not a typical one, but it's kind of simplified for this particular example. In this customer dimension, the customer is the key attribute for the dimension. And this represents the lowest grain that this dimension supports. And from the customer, we've got a couple of ways of aggregating those customers. We can look at customers by income, we can look at customers by gender, or we can look at customers by the geographical region that they exist in. So when we start processing this, analysis services has to process first the attributes in the dimension that have no other dependencies. So in this case, it's going to start by processing income, gender, and country because those don't rely on any other piece of information. It can basically process those in parallel and in isolation from any other attributes. Now, once that set of attributes is processed, it can then process the next set of attributes that have no dependencies except for the items that have already been processed. So in this case, region is the next attribute that we would see being processed. So what this means, if you think about this in terms of how it impacts your processing performance, the more attributes you have that are basically top-level attributes, the more that can start being processed in parallel. However, everything is basically going to come down to the key level, and as you continue processing, the key attribute of the dimension it has to be processed last because every other attribute within the dimension has a dependency, or it has a dependency on every other attribute in the dimension. So as you can see, we finally get down to processing the customer. Excuse me. And one of the things to bear in mind is as each attribute is being processed, analysis services has to hold all the immediately dependent attributes in memory for that processing. So in this case, when we get down to the customer key attribute, we're holding in memory also the income attribute, the gender attribute, and the city attribute. So this is where attribute relationships come into play from an attribute processing standpoint. Most people were aware that attribute relationships, and just to show you what I'm talking about here, let's take a quick look at AdventureWorks. And if we look at our date dimension, just close and reopen that, and go to the attribute relationships. The attribute relationships is where you define the hierarchy of how these attributes relate to one another. So we can see date is at our key level, dates roll up to months, which roll up to quarters, which roll up to semesters, and finally to years. So most people are aware that these attribute relationships impact query performance and can be used by analysis services to prepare better aggregations on the data and facilitate faster querying. They also have an impact on processing. And the reason is that, as we just saw in our example, if I were to process the date dimension, when I get to the point of processing the date key, then I have to hold all the attributes that it has an immediate relationship to in memory. So if I have a dimension that has no attribute relationships and it has 50 attributes, Well, by default, all those attributes are related directly to the key attribute. So I have to hold all 50 attributes in memory while that key attribute is being processed, which can lead to extreme memory usage during the processing of the key attribute. So instead, we do want to have attribute relationships here. They're important not just for query speed, but also for the processing speed, because they reduce the memory footprint that each attribute has to have while it's being processed. So as you may or may not have heard, you ideally want your dimension attribute relationships to look like a tree and not a shrub. So again, make sure that from a best practices standpoint, it's easy to build those things in up front as you're creating the dimension. It can be a little bit harder to add them after the fact. So attribute relationships are particularly important in this particular step of the dimension processing. The hierarchy processing is basically populating the hierarchy store. These do process in parallel, and generally they're not horribly time-consuming. If you have very large dimensions, though, the one spot that can take more time is ordering the members in the hierarchy. So this is using the order by information that you provide on the dimension. We'll take just a quick look at that. So if I look at a particular attribute, I can specify the order by as key name attribute key or attribute name, and pick a different attribute to actually use to derive the order. So having that information can actually slow down the processing of the hierarchy. Again, this typically only occurs if you have very large dimensions. You can eliminate the ordering if it doesn't matter for your purposes by setting the attribute hierarchy ordered property to false, and this is done in the same place. Excuse me. The decoding stores is, again, a set of tables that are prepared that stored internally within the analysis services database that facilitate looking up high-level members of a hierarchy by the ID that is attached to a lower member. So this would give me the ability to look up very quickly the city associated with a particular customer if all I had was the customer ID. This generally does not present performance bottlenecks. It's very light on system resources, so usually no particular problems here. And then the final step for processing a dimension is the construction of the bitmap indexes. So again, these are used to facilitate faster lookups from one attribute to related attributes. These do use the decoding stores that were created in a previous step. So when you're building the bitmap indexes, all the decoding stores for related attributes are physically loaded into memory. This can be another source of bottlenecks when you're processing dimensions. So you can get rid of that memory overhead by setting the attribute hierarchy optimized state property on the attribute to not optimized, and that's going to disable the index. However, this will have a big impact on the speed of querying that particular attribute. So if this is an attribute that's used heavily in queries, you probably do not want to make this setting. But if it's an attribute that has high cardinality to the key attribute, it's closely related, and it's not used heavily in queries, then disabling this can save you some time on the processing side. So as we move into the partition processing, actually processing the fact data into partitions, this is really two steps that occur here. The first is processing the actual data, and then the second is processing the indexes and the aggregations. So ProcessData is broken down internally into three steps. The first step is actually reading the data from the database. This can be done in parallel. It can open up multiple connections to the database in order to read in this information, and we'll talk more about that as we get into some of the bottlenecks that you can encounter. The ProcessData step is actually taking the data that's been read and mapping it to the dimension IDs that have been created in the previous dimension processing step it's also aggregating the data. So when it's aggregating the data, it's looking for what is the grain of this particular partition, and am I reading in values within the set of data that I'm processing that have the same set of granularity attributes. And if it does find that, it's going to go ahead and aggregate those values together. So if you have 6 rows that all have the same grain as incoming information, it's actually going to aggregate that into a single row in what it stores in process data. One of the things to bear in mind with this is it does this in a buffered way, so you're not actually aggregating across the entire set of source data, but you're aggregating for the specific buffer of information that you're processing. And then the final step for process data is it writes the data out after sorting it and compresses it so that it takes up less space on disk. So the primary place where we can affect process data is in how we read the data, making sure that we read the data as quickly as possible. And again, we'll talk more about that as we get into some of the bottlenecks that you can encounter in this process. The processing index step is where all the indexes and aggregations are created. This again has to load up the decoding stores for all the attributes that are related to the granularity attributes for this particular partition. The attributes that are not included in that are the ones that are not optimized. So again, setting that not optimized flag on the attribute can reduce the memory usage, not just in processing the dimensions, but also in processing the facts that are related to those. But again, that can have a significant impact on query performance. So it's one that I strongly recommend you test carefully before you actually roll out into production. Another thing to be aware of when you're processing indexes is if you have large partitions that have lots of aggregations, it is very possible that your aggregations, as they're being processed, can end up being written to a temporary file on disk. And this will drastically slow down your performance. So some of the solutions to this are to split up the partition a little bit. If you absolutely have to split a disk, you want to make sure that you're writing to disk drives that have the fastest speed possible. But ideally, you should avoid this. And we'll talk about performance counter that you can monitor, make sure you're not doing this. And then we'll also talk about a couple of other options for how to avoid this, if at all possible. So when it comes to doing the performance tuning, there's an acronym that I was given by a person that I worked with quite a while back called SMART. And basically this was his pattern for how to do performance tuning. And it's a good pattern, and I've been using it for many years, so I've kept it around. Basically, the first step of doing the performance tuning is set a goal. What do you want to actually get to? If your goal is simply to improve performance, that's usually not specific enough. You can improve performance on almost any system, but what you really need is an understanding of what do I need to improve performance to? What's the size of the processing window that I have available? If it's 30 minutes, well, that gives me a target. I need to, and your current processing is taking an hour, then you have a target of reducing your processing time by half. If the goal is to reduce overhead on the SQL server that's acting as back-end store for analysis services, these are all specific goals, and ideally you want something that's actually a measurable metric in terms of the goal for your tuning process. The next step before you do anything else is measure. So take the system as it is, actually run it with all the same profiling and measurement tools that you're going to use to continue this process. And the reason for that is measuring does change your performance. Performance is typically going to be a little bit slower anytime that you're monitoring things because the monitoring takes up additional resources. So you want to get a solid baseline that you can operate off of moving forward. Once you've measured, take a look at the measurements that you produced and figure out where the bottlenecks are. Once you've identified specific bottlenecks, pick one, the top one, or the easiest to remove. It actually doesn't matter a whole lot. But the important thing there is pick one bottleneck and take that bottleneck out. Make the appropriate changes to work around it. Once you've remove that, go ahead and retest and evaluate again. The important part of this is if you remove a single bottleneck, then you can easily tell what's changed. If you have removed 5 things, or you've tried to tweak 5 different settings, it becomes very difficult to tell what settings actually had what impact. So you want to change one thing at a time, test, evaluate, and then start the process over again. So from a monitoring standpoint, what types of things do you want to measure? Performance Monitor is very handy for looking at your processing, and here's a few of the counters that I typically use. Some of the more important ones here, the MSOLAP memory counters for the high limit, the low limit, and the memory usage. So I'm going to just show a quick example of that. So what we're looking at here is a performance monitor trace that I created from processing the AdventureWorks database. This was run on my laptop, so it's not a particularly interesting trace in this standpoint. But a couple of the important metrics are, again, the memory limit high and low. This is going to tell you what analysis services is set to in terms of memory limits. These aren't hard limits. So low basically says as long as memory doesn't exceed this bar, there's no problems, leave the memory alone. As soon as it exceeds the low limit, then analysis services is going to start trying to clean the memory, but it's not going to be particularly aggressive about it. As the memory usage continues to climb from the low limit up to the high limit, analysis services is going to get more aggressive about cleaning the memory. And if it actually does cross the high limit threshold, then analysis services is going to go into a much more significantly aggressive cleaning mode. From a processing standpoint, ideally you don't want to see your memory usage. In my case, my memory usage for AdventureWorks was almost nothing. But you don't want to see the memory usage cross that high threshold. This leads analysis services to start almost fighting with itself for memory. You've got one process that's running that's trying to evict everything out of memory that it possibly can, and your processing is running, and that's trying to put everything into memory that it possibly can. So as soon as memory usage starts bumping up against that high threshold, it can really have a pretty drastic impact on your performance. So ideally, you will want to configure your processing and your memory limits so that during processing, you stay either just below or just over the low memory limit as being a kind of an ideal target. Some other values here that are particularly helpful, the processing pool, busy threads, idle threads, and the job queue length. So this tells you when analysis services starts processing, it allocates a certain number of threads at this configurable setting on the server to performing the processing jobs. So busy threads tells you, okay, how many threads did it actually use? In this case, I used a maximum of 49 threads. That's below the default of 64 threads, so that's not a problem. However, if I was bumping up against, if this was saying 64 threads, that might be an indication that during processing I could actually make use of more threads, and I might want to up the server setting for that. Idle threads shows how many of these threads are sitting idle at any given point, and you expect that to be idle at certain points in the processing, but generally you shouldn't have a very low maximum number of idle threads. That should be pretty close to the total number of busy threads that you have. And the processing pool job queue length. This says how many jobs have been queued up for processing that haven't actually kicked off yet. And this is usually because, it can be because the system's just catching up with itself. But if you see this going for any significant length of time, it usually indicates that there's not enough system resources allocated to run as many processing jobs as analysis services thinks that it's capable of. So we're going to look at, as we go into the bottlenecks, we'll look at a few of the settings that we can address around these things. But those 6 settings are some of the simpler ones to look at and have actually quite a bit of information in them. Certainly, as we flip back to the slide here, there's a lot of other items that you can look at. The temp file bytes, writes per second, that one will tell you whether or not any of your aggregations are actually spooling to disk or not. So it's another important one to look at. And then two, you may want to monitor on your SQL Server memory usage and performance through perfmon. The other tool that we tend to use for monitoring analysis services processing performance is Profiler. So we can profile both the SQL Server side. Here we really just care about the T-SQL statements that are being executed, so the SQL batch completed, and we want to capture the planned statistics for that, so that if there's any tuning needed to those procedures and to the T-SQL being executed, we can actually capture that and have some information to use to tweak it. On the analysis services side, there's a few events that we really want to monitor. The command begin and end are going to capture the actual processing commands that get executed. So those are useful to see when the processing command was issued, when it finished, and the exact details of it. And the progress reports are useful basically for tracking the duration that individual objects took to actually process. So what I'm going to do, just as a quick sample, I'm going to start a couple of traces that are configured on these events. And I'm going to process my AdventureWorks database. This doesn't take very long, but I'm going to actually go ahead and move on with a couple of other things. While we're waiting for that to finish, it should take about 2 or 3 minutes. The important thing with the progress report is that that's going to give you the information on the individual objects that are being processed. So you can look and see what is taking the longest in my processing. Is it a specific attribute? Is it a dimension as a whole? Is it a particular partition? You can get to that level of detail if you capture the progress report information. And capturing the errors is useful in case there are any errors coming up during processing. So when we're tuning, you typically want to run processing in 3 separate steps. You want to process all your dimension information up front. You want to process the data for your partitions as a separate step, and the process indexes as a separate step. You can do a process full on your partitions, and that calls process data and process indexes under the covers as a single operation. However, the SQL CAT team has done some testing. SQL CAT is the customer advisory team for SQL Server, and they work with some of the very large implementations of SQL Server at various customers that Microsoft works with. And in their testing, they found that calling process full was often slower than calling process data and process indexes separately. It's not universally true, but in a lot of cases it was. So definitely my rule of thumb is start by doing process data and process indexes separately, and if you want to change it to process full, then test it first. Also, make sure you're using the most appropriate processing type. If you have the option of just doing process indexes because the data hasn't been processed, you should definitely do that. For the tuning process, though, you want to make sure you're processing in a consistent manner so you can actually compare apples to apples between each one. And generally, when we're tuning, we want to shoot for a CPU utilization of 100% throughout the tuning, throughout the actual processing step. The reason that we're shooting for 100%, a lot of people think 100%, I don't want to max out my CPU, But from a tuning perspective, if you're hitting 100%, you basically max all the performance that you could possibly get out of that machine. If you want to go get any more performance, then you have to upgrade to new CPUs, which typically is a fairly significant undertaking with most servers. So that's why that's kind of a good target. We've eliminated any other bottlenecks. We know it's just purely down to the hardware if my CPU is maxed. This is more of a theoretical target for tuning. It's actually very rare to actually be able to hit 100% CPU utilization, but it's certainly a good goal during the tuning process. So I'm going to switch back. Let's verify that our processing has finished. And if we take a look at the profiler, this is the profiler that was running for analysis services. So we can see we have our command that actually executed our batch for processing. And then we have the progress report begin, which indicates when each item started to be processed. And we have the end, which indicates when each item finished processing. And if we look over, we have a duration column that tells us exactly how long each of these items took. And if we look at on the other end, we can also see what we were profiling against our SQL server, so the statements that were being run as well as the statistics for those. And we'll talk about some tuning that we can do for that in just a couple more slides. So again, I'm going to reiterate the warning, change one thing at a time. Most settings that you can change have trade-offs. As we mentioned before, setting the optimized state for a attribute may improve your processing performance, but can hurt query performance. Most items are going to have both a positive and negative effect. So it's very difficult to say this is a setting that you should universally make. It's all very dependent on what part of the system is most important to you, where your precise bottlenecks are. So understand the effects of the setting, test each one in isolation. If you change 4 of these simultaneously and processing remains the same, then you start having to ask yourself the question, well, did one of these have a vast performance improvement and the other 3 offset it because they made things slower? You really want to change just a single item, verify that it's getting the desired results, and then proceed from there. Or perhaps you change the item, you realize this isn't improving performance, so you go ahead and undo that change. So some specific bottlenecks that we tend to hit during dimension processing. Number 1, data retrieval. Getting data out of the SQL server is often a slow point of this. And I shouldn't say SQL server. This really applies to any source that you're using for your analysis services database, or as a backend for your analysis services. The advantage here, the quick fix, add indexes to the tables that are basically tuned specifically to get data out faster for analysis services. That's probably the lowest impact solution to this particular problem. From a surgery standpoint, and again, surgery this is major if you've got a deployed cube that you're trying to improve performance on. This is actually relatively minor to do up front if you build it into the design of your cube. Go ahead and use SQL views to support the dimensions. So the advantage here is if I've defined a view that I'm querying from analysis services, so I'm not hitting the underlying table directly, but I'm hitting a view, then if I need to do more advanced tuning, I can actually go in and tweak the SQL for the view. It doesn't really have any impact on analysis services outside of it just gets the data faster. But I have much more flexibility to add query hints, to do tuning if I'm in full control of the SQL that's being executed. If I'm hitting a table directly through analysis services, then I have less control of the SQL that's being executed. So definitely recommend SQL views as giving you the most options for improving the query performance for processing dimensions. If you're hitting any bottlenecks while processing attributes, The number one thing you can do is reduce the number of attributes. If it's not there, you don't have to process it. It takes no time at all. The other thing to do is make sure that you have attribute relationships. I can't emphasize the importance of that enough. Obviously, huge impacts from query standpoint, but also very good impacts from a processing standpoint as well. If you have attributes, again, that are not key to be queried on a frequent basis, and they have a high cardinality when compared with the key attribute, then setting those to not optimized can save you a significant amount of time during the processing. And you can also set the attribute hierarchy enabled to false for things that are more truly member properties that aren't included in a actual dimensional hierarchy fashion. When you're processing the data for your partition, there's a couple of bottlenecks that you can run into there. The data retrieval is, again, one of the bigger ones with this. So from a Vantage standpoint, adding indexes to your relational source can be good. If you're using SQL Server or another database engine that supports compression, this can also often give you faster data access, specifically because in many cases the I/O system is the bottleneck for getting the data out of the relational source. So compression lets you read the data off disk faster because there's less of the data to read off disk. However, if you're in a CPU-bound situation, this may not be the best option to enable compression. You can add locking hints to reduce the amount of resource utilization on the relational server. I'm not a huge fan of tab lock, but it's one of the options here, and I'm sorry, tab lock is actually fine. I'm thinking of a different option. So if you do a table lock as an example, that reduces the amount of locking information that SQL Server has to keep track of, and will reduce the overall resource utilization on the back-end database server. The other thing that you can do here is add database connections. So by default in analysis services, when we look at the data source, there's a setting here that is going to, sorry, let me see if I can get rid of that real quick. We have a setting that is going to specify the maximum number of connections. So this is part of the data source setting, and this controls how many connections analysis services will open to the underlying data source. So if the data source can support it, having more than 10 can be good, because that allows analysis services to run more than 10 queries simultaneously. Close my magnifier, and we'll go back in here. So adding database connections is relatively straightforward, again, assuming you have the resources and can vastly speed up the processing of the data side. Things that are, again, an impact at a much higher level, easy to do during design, much more difficult to implement after the fact. Number one, make sure your relational and analytical partitions are aligned one-to-one. So this, again, depends on having an underlying relational store that supports partitioning, but ideally you want to make sure that your relational partitions has the same information that you plan on having in your analytical partitions, and that can really facilitate better processing speeds. Making sure your data types are the smallest types available to store the data also can improve processing speeds, because it means moving less actual data. So that's, again, relatively major change if you've got a system in place, but as you're designing, make sure you don't over-allocate on the size of the data types. For example, using a big int where a regular int would suffice. And also look at how much how the database server is doing from an I/O perspective and from a network perspective. These can be bottlenecks that often are a little bit out of your control from if you're administering analysis services, but certainly if the database server can't get the data off disk very fast or can't push it over the network, analysis services can only process as fast as it gets the information in. Another bottleneck that you can see with processing data is an underutilized CPU. So this is where some of those counters that we looked at earlier come into play. If your job queue length is greater than 0, then check your processing pool idle threads. So again, the job queue length being greater than 0 means analysis services wants to process more, but it doesn't have any available threads to do that processing. So if it wants to do more processing, but the number of idle threads is 0, then you can go into your analysis services advanced settings and set the max threads property under the thread pool process area to a value greater than what it is. And let's take a quick look at that. So you just go to the server, the properties, show advanced properties. And we want to look at our thread pool and our process min threads and max threads. The value defaults to 64. Particularly if you're on a big server with a lot of CPUs, you can often increase this and get better processing performance. So if the idle threads is greater than 0, this indicates a different problem. It's not that there's not enough threads available, it's that there's not enough job coordinators. So in analysis services, when it's doing this processing, it has job coordinators that basically manage the process of doing processing. And this is set in the same dialog under the coordinator execution mode. So you'll notice that this is set to -4 by default. The fact that it's a negative number indicates that it's a per core setting. So this on a dual core machine, this means that you can have 8 coordinators. On a single core machine, this would mean 4 coordinators. If you set it to a positive number, you're then configuring an absolute number of coordinators. So by setting this to 4, then we may be limiting the amount of processing that can be done by only supporting 4 coordinators. So again, in the case that we're seeing a job queue length that's greater than 0 and idle threads greater than 0, then we may actually want to change the coordinator execution mode to something like -5 or -6, rerun and see if that actually helped resolve some of the bottlenecks. These are settings that you should be careful with. They're under the advanced properties for a reason, so don't idly change these, and please do benchmark the effect of each change. And again, from a surgery standpoint, increasing the number of partitions in your different measure groups can actually give you some of the same results, because analysis services is automatically going to consider multiple partitions. It's going to use multiple threads to address those, and this can often speed up processing without you having to mess with any of the more advanced settings. On the process indexes step for partitions, one of the problems here is just not having enough memory. As we mentioned before, you'll see that counter for temp file bytes go over 0. What you can do here is try to reduce memory usage. So this one goes back to reducing the amount of decoding stores that you have to have in memory, which means setting attributes, either removing attributes that aren't really being used in the queue or marking them as not optimized to take them out of the memory footprint during processing. You can also decrease the amount of parallelism. So this is definitely one of those settings that has potential negative impacts as well as positive impacts. By running less simultaneously, you're not using as much memory, and you may actually be able to fit the aggregations into memory because you're only processing a partition at a time instead of 5 partitions at a time. However, this is likely to also increase the overall amount of time that it takes to do processing, so your mileage may vary pretty drastically on this one. If you absolutely have to spool the aggregation information to disk, then make sure that the temp dir setting for analysis services is pointed to the fastest disk that you have available, and that will reduce the impact of that. And then adding physical memory is always a workaround to any lack of memory problem, assuming that your server is not already maxed out. During process indexes, if the CPU is underutilized, this has actually the same rule as we were looking at during process data. You may want to increase either the max threads or the coordinator execution mode. You can also increase the setting for the aggregation memory limit minimum, which tells analysis services to use more memory when it's creating aggregations, which will have the effect of giving you a little bit more CPU utilization, but may also conflict with the setting that or the option that we were just looking at, where aggregations are going to take up more space in memory and thus increase the likelihood of spooling the disk. So you don't want to go too far with that particular setting. And again, increasing the number of partitions here can have introduce more parallelism into the processing and increase your performance. I/O I have as a separate category. I/O is one of the bigger bottlenecks that I tend to see, and probably the most common. Some markers for this: if you're monitoring performance, if you're on a SAN, then go to the SAN people to understand if I/O is an issue or not, and that may be challenging. It's good if you're managing a large analysis services implementation. Make friends with the SAN people, buy them a beer now and then. Make sure that that you have a good relationship there, because you really need to work with them to understand the characteristics of how analysis services is using the SAN and whether they have the best setup or not. If you're working on local disk, then using the perfmon counters for disk queue lengths, reads and writes, can be helpful to determine if that's actually a bottleneck. There's really no quick fixes here other than making sure that you don't have other processes writing to disk at the same time. For example, having your SQL Server, relational engine, and your analysis services database using the same set of disks actually sets up significant amounts of disk contention, because you're requesting data from SQL Server, which is forcing it to read off those disks, and then you're writing the data back using analysis services. So that can create some definite hassles when it comes to the disk contention. So you want to avoid that if at all possible. From a surgery standpoint, increasing the number of disks that you have, going with faster disk is good. Short stroking disk refers to basically only using the outer part of a disk in a traditional rotating disk. The outer part of the disk rotates faster, so by skipping the inner portion you get faster speeds, but at the cost of not actually being able to leverage the entire amount of disk space on the disk. Solid-state disks are one of the few silver bullets when it comes to analysis services processing. If you have the data that will fit on solid-state, that can have a tremendous impact on your processing performance. It can also have a very positive impact on query performance. So if you can afford it, it's definitely worthwhile. So just a couple of final thoughts. Tuning takes a lot of time. Don't plan on sitting down and working through 50 different options in a couple of hours. If your cube is big enough to worry about tuning the processing performance, then you need to allocate sufficient time to, again, make a setting, run the processing, see what the results are, then make a new setting, run the processing again. So don't set out to do this in too short of a time. Allocate plenty of room for it. Make sure you have clear goals and revisit those goals along the way. If you don't know how fast the processing needs to be, then you can basically spend forever doing the performance tuning. I think I've probably hammered on this enough, but one more time, just for emphasis, change one thing at a time. Don't make multiple setting changes at the same time, because it will confuse things as far as which setting's actually having the benefit. and make sure you document along the way. It's not at all uncommon as you're doing performance tuning to realize you need to roll back 3 or 4 steps to get back to a state and try a different path. So if you haven't been documenting, you may inadvertently leave a setting in its new state instead of rolling it all the way back to the original state. So make sure you're documenting the changes. A couple of resources that are really valuable. One, the Analysis Services Performance Guide has a lot of great advice for tuning your processing performance. It has some very nice flowcharts for that. So highly recommend that if you haven't read that in depth, definitely do so. The SQL Cat team, as I mentioned, has a great website with lots of resources on analysis services. And then I have some information on my blog, and again, I'm available via Twitter or email if you have any questions on that. Okay. Rachel, did we have any questions?
Hey, John. John, yeah, we did. We had about 10 questions. If you want to go through those quickly. Sure. Let's see. For a very large fact table, how much memory on the server per number of rows?
That's a great question. It really depends on the width of the rows in the fact table. So a little challenging to just give an immediate answer to that. I would generally look at how large the partitions that you're setting up are and do a rough calculation of, depending on row size and how many rows are going to be in each partition, ideally you want to be able to fit all of that into memory with probably roughly a 2x multiplier for other things that are going on.
Okay. Is there a baseline for processing a cube based on the size of a fact table?
I'm assuming that means like a baseline performance metric, as in if my fact table is 10 gigs, then I should be able to process the cube in an hour. Unfortunately, there's really not, because hardware variances are so great, and hardware has a really significant impact on the performance. So I wish there were actual rules of thumb around that, but there's really not, because of the variances that you tend to see between different sets of hardware and different environments.
Great. Okay. Are indexes necessary, and do table partitions on the fact table help with performance?
So on indexes necessary, they can definitely be helpful. So particularly, a lot depends on, again, the specifics of your environment. But if you're basically running a query that's going to create a table scan in any case against your source data, then indexes aren't necessarily particularly helpful. However, for dimension processing, and if for larger cubes, if you're processing individual partitions, you're typically at that point not leveraging table scans. You're going to hit an index to get a filtered set of data. So they can absolutely be a benefit there. So you don't want to go crazy with indexes. That can slow down the writes to your fact table, but they definitely can be beneficial. And the second part of the question, could you just repeat that?
Actually, I've already put it in the recycle bin. Sorry about that. Guys, all the questions, if John doesn't get a chance to answer before we end the session, those will be sent to him, and he can send those out to you via email if there's wasn't a question that didn't get, we didn't get to answer.
Okay, I just remembered the second part was, what are tables or table partitions in your relational source beneficial to analysis services? Yes, they absolutely are, particularly as I mentioned, if those partitions in the relational source are aligned with the partitions in analysis services, that can be very beneficial, because in SQL Server specifically, if you have partition tables, that lets you use more threads to read from those. The partitions in analysis services also have more threads allocated, and if they're one-to-one, it generally lines up really well from an AS perspective.
Okay. Bill wants to know, do you recommend forcing attribute relations relationships even if it requires using composite keys? Why or why not?
I generally do recommend that, even if there is truly, so the key thing for me is there truly a one-to-many relationship between these attributes? Forcing it, if there's not truly a one-to-many relationship, means you're creating something somewhat artificial. So with the caveat that there is a true one-to-many there, then yes, I absolutely advocate it. There are some exceptions to that, though. So if I have a very large dimension that has a lot of attributes and I'm having performance problems because there are not enough attribute relationships in it, then you might create some artificial combination keys in order to create that true one-to-many relationship. I try to avoid that, but for performance reasons, you may not be able to work around it. So my why or why not basically on that one boils down to, if it's required for performance, then you might have to go that route.
Okay, let's take one more question, and those that we didn't get to, I will send those to John, and he can send out that information to you via email. Let's see, Matthew would like to know, how do you deal with processing dimensions with a large amount of rows?
A lot of that depends on where the bottlenecks are coming in. So if the bottleneck is, again, getting data out of the database, look at indexing the database. If you're using SQL views, it means you can much more easily tweak the syntax used to pull that data. In large dimensions, the other common problem is that the dimension attribute relationships, if you look at it like a tree, it looks more like a shrub than a tree. You've got a lot of attributes related directly to the key attribute. And as I mentioned, during processing, it has to hold all that stuff in memory at the same time. All the immediately dependent attributes that are referenced from any given attribute have to be in memory. So make sure you have good attribute relationships on it. If it's a large dimension and it's got a lot of attributes, the other thing to look at is, can you eliminate some of the attributes? You can use member properties to still store that information in the cube if needed, but it's not optimized for query purposes. Obviously, you can't slice and dice on those things without doing some MDX, but it does reduce the overhead in processing, so it can be a good alternative if you just need the data available, but you don't really need to slice and dice on it.
Great. Okay, John, I think that will end us for today. It's almost 12 o'clock, and thank you again for your session on Advanced SSAS. And just a reminder, everyone, our free training session is recorded and will be available by the end of the week for your review. And check back with us on Thursday. Thanks so much. Have a good day, John.
All right, thank you.